right. Good afternoon. My name is Ali Kujuri. I'm an adjunct professor at the Engineering Science Department and one of the organizers of this lecture series. I would like to thank Mr. Shahrad Jamshidi and also Kate Lab who helped me organizing this series. On behalf of the Engineering Science Department and the School of Science and Technology, let me thank you all for attending this third lecture in the series for this academic year. And believe it or not, 150th lecture since we started in 2006. Before I introduce our guest speaker for today, let me mention that pizza will arrive at 5:30 of the lecture. And the next lecture will be on October the 17th, and the title is A Smart Environmental Monitoring Using Low-Cost Sensors and Low-Power Wide Area Network by Dr. Nansung Wu from the Engineering Science Department. Our guest speaker for today is Dr. Shahrad Jamshidi, and the title of his talk is Machine Learning. Dr. Shahrad Jamshidi is a data scientist and co-founder of at the Australian startup Remy AI, which in fact a startup, as I mentioned, and he works remotely in Santa Rosa, where he implements different machine learning algorithms on a wide range of consulting projects. He received his doctorate in applied mathematics at the Freie Universität Berlin, Germany, and his bachelor's degree from University of Sydney, Australia. His collaborations with biologists and ecologists during his graduate research pushed him in the direction of data analysis and machine learning. So here is Dr. Jamshidi.
Hi everyone. So yes, I work for this Australian startup, Remy AI, and so it's actually me and a few friends from high school, and my colleague did a master's in philosophy, but in logic and artificial intelligence, and then I was the coder, he was the visionary, and then we founded the company and have grown from there. But yes, I'm working remotely, just out of Santa Rosa, sometimes even on campus here, just to change it up a bit. So I want to just introduce some concepts of machine learning, just so you can get an idea of what's possible nowadays with data. Okay, so I'm going to introduce some overarching concepts of machine learning. It's a very big field, and it's very hard to break it down and simplify it too much. So it's a very broad topic. So in general, you have machine learning has various methods, and they are simply algorithms that are taking lots of data and being able to get some kind of useful feature out of it, some kind of structured information. And just to give you ideas or where you might have seen this in the day-to-day world. So you have some applications in image recognition, so optical character recognition, how to convert an image of a document into text. So a machine can identify where text is located in an image and then transcribe that text into a string format. Face recognition, so on the new iPhones are able to recognize a person's face and then instead of the Touch ID. But there's also at passport control. In Australia, you line up at a kiosk, scan your passport, and then go to a booth. They take your picture, confirm that it's you, and then let you through. So complete automation of the passport control. One time I showed up with a bit of a beard, and it said, I'm not sure. They sent me to an actual person. Then object tracking, so trying to track an object over multiple frames of a video. And this kind of technology is practical in Amazon Go, the shop where you scan your, when you walk in the store, you present your Amazon account, walk through a store, grab items, and then leave. And then they'll charge your Amazon account. And so they're tracking, using image recognition, your movement through the space and what objects you are taking. And that is still a big open problem because I believe the first version of Amazon Go, they could only track accurately 9 people in the store. And then with more research, they were able to get that up to 30. But yeah, it's an ongoing challenge. So that was image recognition. You have language processing. A computer does not understand the words that we actually say. It understands programming language, but not natural language. So it is a challenge to break up the sentence into words and then identify what is the verb, what is the pronoun, what is the article. How do they combine together to show a dependency of each other? And so you have parts of speech tagging to distinguish which word is a noun, which word is an adjective. Then from that you can also determine certain entities, so like geolocations or names of people, names of companies. And then of course with language processing comes the personal assistance. You give a textual command, they process what you are trying to ask, and then they will perform some actions to achieve it. And another, continuing with the personal assistance, you have audio-related analysis, speech to text. The way my accent and my pronunciation, that's something that the Siri or Alexa has to learn over time, and it's very different from how another British person speaks, or even someone with a German accent, I don't know. And if you've ever played around with the language settings on your phone and changed it to another language and then tried to speak, you see what it transcribes. It's very, very interesting. Just saying an English phrase and what it will transcribe to in German or in French or something. It's a challenge, and also trying to block out noise, block out a passing ambulance or something. Text to speech, so making it sound less robotic, less like Stephen Hawking's, and trying to get correct intonations and melody and flow when spoken. Audio fingerprinting, so being the idea of Shazam, being able to identify from a small snippet of an audio sample which song is this song that is being played. Some other examples, of course, autonomous cars, so combination of image recognition and sensors, try to come up with decisions on how to move a car through and obey road rules safely. Smart appliances, these are to IoT devices like the Nest thermostat, which is probably the easiest example, where they are trying to learn your routine, and then learning your routine, they can predict and anticipate what you're going to be doing, and so they will adjust the thermostat setting so that they're ready for you. Recommendation engines, so given lots of customer data, knowing that people who grouping together common items that are being consumed, and so being able to recommend immediately and the next item to purchase or the next item to put in your cart. Personalized advertising, this is where it gets kind of big brothery, where, again, not only trying to determine your personal customer routines based off what other how you consume, just in general. So they have been able to determine to almost to the week how far along some women are in their pregnancy based on their purchasing. And so if you can anticipate that they're going to be buying this in the next week, then you can already throw sales and discounts their way so that they would shop at their store. And along the lines of, if you can predict someone's routine, you can also predict something that's outside of your routine. So if you have very clear transactions going to this cafe and then this, that toll booth and this restaurant, and then all of a sudden you get a transaction somewhere on the other side of the country, then an AI can pick that up quickly and stop it happening. Okay, so those are some various applications. Hope that was more to give you an idea of the motivation of what's possible with data. And now I'm just going into the actual, the different methods that are out there. That is what algorithms are being used to process the data and actually achieve these feats. So I consider a lot of the machine learning methods, the algorithms, to be separated into these three main branches: supervised, unsupervised, and reinforcement. And I'm going to go through the overarching concept of each of those and then some example methods for each of those. So starting with supervised learning. We have on the right here, imagine that to be a spreadsheet of data. And with supervised learning, you have a certain target variable. So say, for example, you want to predict if a person has or does not have a certain disease, or predict the stock price in a week's time. So that's a target variable that you're trying to predict, and then you have the other data points of input variables. So for the example of predicting a disease being present or absent, and so a person's are they smoking, non-smoking? Are they what's their age, their weight, their height, their so forth? Just some other input data that is matched to that target, so that you can bring in an unknown person's credentials, and then already try to predict that output. So with this, the input data and the target variable, you have a labeled data set. And then in supervised learning, it's good practice to split it between training and test. So you want to generalize this as much as possible. So, or use the example of the face recognizer. You can't show it every face in the world, but you want to show it enough faces that it will get the idea and try to predict where a face is. And so you train it on only that majority of the data, and so you run it through this algorithm, and then it will spit out a prediction, and then it will look at the prediction and look at the actual and say, I got that wrong. Let me update how I've processed the data to achieve that. And so it learns, and the algorithm has some learning built into it to improve that prediction. And then with the test set, because it hasn't seen it before, it shows how well it generalizes the task at hand. How well does it predict locating faces? And so you put the input data from the test set through the trained model, you get a predicted output and how accurate it is, and then you can determine the accuracy and say how confident the model is. So that's what supervised learning is doing, and you're trying to, the algorithms are trying to find the patterns that will help best predict the target variable. And some examples of these are naive Bayes. So you have, this is a probabilistic method where you're just looking at the probabilities of a target the probabilities of the target variable having certain values, the probabilities of input variables having certain values, and how they relate with each other. And then using Bayes' theorem to just flip that over to say that, to give a probability of a certain target given a certain input. So that's the application of Bayes, and naive is just saying that each input variable is independent, is unrelated to every other variable. Decision trees is like a flowchart of where, so this is the outcome, but imagine you have this set of data where I believe this is the absence or presence of disease. I'm pretty sure the start is the start of a certain treatment, and the age, I'm guessing it's of a cat or a dog, because that wouldn't be years in human years, I can't imagine. Oh, who knows? What's the... So we have the absence and presence is the target variable. The start and age are the input variables. A decision tree is looking at the data and saying what is the most efficient way, what is a single variable, and a threshold that will most efficiently split up the absence from presence. And so the first split is at that. At this start is greater than or equal to 8.5. So then you separated the data set between these two sections, above 8.5, below 8.5, the other way around. And then when you have two smaller data sets, you do the same thing. It's a recursive method. Just do the same thing, and you can start to build a decision tree so that when you get new input data, you just run it through these decisions, and then you get a probability of whether the disease is present or absent. Random forest is an extension of that, where you're just you're removing some of the input variables, generating many more decision trees, and then trying to overlay what was the common theme when I removed certain variables. Well, what are essential variables? What are essential decision points? Neural networks are inspired from neurons in the brain. You have a neuron that usually has an active or inactive state, and whether it's active, it depends on the weighted inputs of activations of neurons that it's attached to. So if we think of the active state being 1 and the inactive state being 0, then we try to find, then the input activation needs to pass some certain threshold, theta, in order for it to be active. And so the input data has a certain activation. You multiply them by weights and feed them into these hidden nodes, which act as neurons. So we'll see, is there enough activation to activate that one hidden node versus not? And so then you might have, with a certain set of inputs, that you have this one is active, that one is inactive, that one is active, that one is active. And then again, you pass those, you multiply those by more weights and try to determine the activation of the output or target variable. And then if that's, and so that's how the data is propagated through a network, and then the training of it is using numerical methods to improve the error. So again, you feed it with supervised learning methods, you tell it what the target is, this is what it predicted, let's find ways to change the weights so that this will be a better overlap. Okay, so those are some examples of supervised learning methods. Again, you have the input data mapping to a target variable. unsupervised learning is when you don't have a target variable that you're trying to predict. So you just have a scatter of data, scatter of points. So what unsupervised methods are doing are trying to bring group common points together to try to see if where are there clusters of points that are close by. It can be seen as they are usually something to do with a feature extraction or a dimensionality reduction method. So you have a higher dimensional data set, many input variables, and you want to see how they're related. Sorry, one step back. With you're able to combine unsupervised with supervised learning to get more deep learning, where you're trying to reduce the number of dimensions that the supervised learner is actually looking at, so it can make better decisions, or the algorithms might be able to run more efficiently. Okay, so yes, unsupervised learning has no target variables. Here are some examples. K-means is you're looking for k numbers of clusters, k groups. You start with just a random allocation of each data point belonging to a certain cluster. Then you calculate the centroids, and they'll probably all be very close to each other. And then, because given all these data points and it's randomly allocated, you'll get points from all directions, and so the centers of each of the three clusters would be very close to each other. But then once you have those new clusters, those three clusters, then you can reallocate the data points given its proximity to those centroids. And then with that new reallocation, you update the centers of those clusters, and you just recursively do that until you converge. And so yeah, you get something like that, where you can see how the data was generated with two smaller variance balls, and then this one with a slightly larger variance. And you see that a more efficient line would have been, a better line would have been somewhere here that separates out this cloud of clusters from this cloud of data points. But okay, it's still just running an algorithm and doing it the best it can. Hierarchical clustering. This is where you want to build a hierarchy of the clusters. You don't tell it how many clusters to look for. It's just like start to group them together, and at what stage does it become one big cluster. So this can be done top down or bottom up. So start with the big cluster and then slowly see at what stage does one break off. Start with the big cluster, and then at a certain distance, one data point breaks off from the rest of the cluster, and then at another step, two clusters form from that one larger cluster, and so forth. But you can also do it the other way around, so starting with just the individual data points and then slowly increasing the distance until you group items together. And this can be a good way of determining outliers. So you know that you just tell it what threshold you want to have for clusters to be close together, and then you identify something that's outside of the normal scheme of things. The association rule. This is where at least one method to for a recommendation engine. You have just consumer data of multiple purchases for a single shop visit, and you start to group certain items together because they always seem to correlate. When one person buys this, then they often seem to buy that. And so I always think of the Netflix example. So with a lot of people that seem to like, I don't know, a romantic comedy, also like this certain drama, that also like this other movie in the similar genre. And what the association rule is doing is just kind of seeing that, okay, there seems to be a big group of movies that are close, that always are brought together. And so that this can be its own genre, but they can't label it like that until they actually go in and see what's the common theme with those groups of movies. Yeah, that's all I wanted to say about that. Okay, so that's unsupervised learning. Those are some examples. And the final machine learning method is reinforcement learning. And this is where you don't have a complete data set, but you're gathering data and learning as you go, because you are interacting with an environment. This is many applications in robotics. So robot is moving through a space that it doesn't know and realizes, oh, I shouldn't go there, I shouldn't go there. Yeah, so it's taking observations from the environment, trying to perform actions based on those observations, and then it's in a new state, observe its environment, and keeps performing actions. So yes, it's mostly used when playing. It's the ones used when playing games, basically. But you can, if you define the game as something that's practical, then like how to optimize your inventory, and so what's the best way to place orders and place orders so you don't get bad punishments or lost revenue from stockouts. Okay, so if you imagine this simple maze, you have the mouse trying to get the cheese and avoid the trap. So you tell the agent where it is roughly in this space, and then it can move around or just react with respect to where it is. And so in this case, it's just move up, down, left, right. And over many iterations of playing this game, it will start to learn what an optimal strategy is, an optimal policy. And oftentimes this the algorithm has an element of exploration and exploitation. So exploitation, I know that this is going to give me a reward, so I'm going to do it. Exploration is like, maybe there's a better solution. I'll go around the corner and see what happens there. Q-learning is one method of achieving that. And there it's saying for every state and action, define a Q value. You initiate all possible Q values at 0. Run one time through the game, and then keep track of what you've done and the final reward. And then once you've gotten the final reward, back propagate that final reward in a certain way through your actions, and then repeat. Do many versions of the game, and then you will slowly start to the Q values that you've assigned to each state action pair will provide you with an optimal policy, because you can kind of think of it as a projected reward. If you're in this state and you go right, then you're going to get the reward. So that reward just propagates back. Reward and punishment propagate through the Q values. Monte Carlo tree search is one that was used in the Google's AlphaGo. So in the context of games, you have the game tree. That is, for every player, they have a number of actions. Based on those number of actions, based on whichever action that player gives, the next player has another set of actions. And so, despite increased computational power, you can't exhaustively search the game tree for Go. I think now you can exhaustively search the game tree for chess, but Go was still it was just too big, too many options. And so Monte Carlo tree search is looking at a reduced space, a reduced game tree, saying, okay, you have player one. You have 3 different actions. Let's just try to optimize those actions. And then based on what the game tree has, the scoring of the game tree, you select actions to get to an end node of the subtree, and then add another element, a new action to that subtree randomly, and then simulate randomly to the end of the game. And then the simulation ended with a loss and the one game, and then you propagate that back up to know that, to give a score for each action. So it's more just keeping track of, it's a way to keep track of the many iterations of a game. Okay, and counterfactual regret minimization. It's an extension of regret matching. Regret matching is a simple method where you know that an action that you took, you know what you get the reward of an action that you took, but you also know if I had taken the other actions, I would have gotten a better reward. So you have a positive regret for not choosing action B over A. But that's for a single action. Counterfactual regret minimization is when you're propagating that regret over many actions within a game, and that is the method that has made a poker AI beat some good human players. Okay, so as a summary, you have that the machine learning methods can be put into these 3 different, the core machine learning methods can be put into these 3 different classes. Supervised learning, where you have a target variable that you're trying to predict. And you're telling it, try to find whatever patterns in the input data to get the best output, the best target. Unsupervised data, there's no target, but see what you can make sense of in this data set. And then reinforcement learning is the getting actions and rewards. And a lot of AI is a combination of, current technologies is just a combination of all these elements, where deep learning can happen where you've apply unsupervised learning with a supervised at the end. You can also do a supervised learning to train the Q values for reinforcement learning, or there's many ways to combine the different core methods and come up with some really amazing technologies. And that's all I wanted to present. Any questions?
For text to speech, basically there's more information in speech, all right? Because it has some pauses, and then there are sometimes when you stress on the word, whatever. How is this basically now, done when you go from text to speech, and then you need to basically go and then probably go and do some work on it to make it what you want, right?
Yes, I mean, I haven't worked specifically in the audio side of things. I'd like to, but it's so you're just given the strings of words, and you might have a sound bite for them, but how to take that one sound bite of 3 words and try to get them to meld together so that it sounds more fluid. That's the bigger challenge, to make it sound more like how we talk, not like robotic.
Yeah, and in fact, going from speech to text, that becomes, in fact, I mean, text would not have that much information as the speech, right? Because when you talk, right, no matter whether I stress or basically pause and so on, it's not.
It's going to convert. Yes, exactly.
So
you lose it. Yes, I see. You lose information because of the intonations and so forth. Yes, but that's why personal assistants aren't trying to determine your emotion. They're just trying to determine a factual thing, and that's why it's limiting. But I'm sure that there's like a project to make the speech to text more sentimental. So like within language processing, there is the idea of sentiment analysis. That is given someone's review or given someone's email, determine if it's positive or negative. Is it like, oh, great job, nice work, or is it like, you should have worked on this, what's going on? So you're right that something is lost going from speech to text, and I wonder if I can imagine there's a group somewhere out there that is actually working on it.
The other question that I have is that certainly the number of pixels in an area of a photograph, right, basically would make it easier or probably not easier to find an object in that picture, right?
Yes.
So is there any shall we say, anything that you need to, any requirement for the number of pixels per area? Or?
So it's, well, yes, of course, it needs to be enough to distinguish. But you can also generate data, given that you know the object of a person, then, so say you're trying to identify a face, and then you superimpose that onto an image, but you shrink it down till it's just however many pixels. And then if at some stage, and then you train the algorithm on it, trying to recognize it with the various sizes, and then you will notice that there is a certain size where it can't recognize it anymore. But because of that greater variability and providing more examples, a machine trained on images is better than sometimes than humans. Because humans aren't used to looking at just the pixelated parts of an image to identify a face. And it's, for those cases, the computers have become better because they know what to look for, and they've been trained on those things. I'm sure that if we ourselves trained ourselves on bad resolution images of people's faces, we'd be able to recognize them, but we're not trained on those. Yes?
Do you have an example of a machine learning algorithm that is making use of more than one of the core methods?
So the AlphaGo? AlphaGo definitely is. So there it's using, it's actually using an image recognition. So Go is, you have your grid and your location of white and black nodes. And that's very visual. And so it takes as an input that image, then tries to process it for, okay, what actions are most probable. And it first applies a supervised learning based off expert expert moves. So it's like given all the moves that are available from past games, it just studies those and says, okay, given this state, an expert chose this spot, and it tries to predict that. So that's the supervised learning, trying to predict where the next move will be by an expert. Then they introduced a reinforcement learner to try to beat that supervised learner. So in that, there it's already just, so the reinforcement learner is just starting to just get better and better once it realizes what the technique of the supervised learner is. So then eventually, because the reinforcement learner is improving its technique. Once the reinforcement learner starts to beat the supervised learner, then that's the new supervised learner, and the reinforcement learner continues to train against itself. And of course, they can play millions of games within hours, as opposed to humans that take a much longer time. So that's one example. But there's this new, the newest push of AI is also this idea of adversarial networks. You have two networks. One is trying to generate, let's say, an image, and the other is trying to determine was that human generated or computer generated. And so they're just kind of sparring partners, and each of them are training against each other. And it's pretty amazing what kind of outputs they get. There was this one really cool one of who was it? There was an award ceremony. Jennifer Lawrence was giving a speech, and they superimposed Steve Buscemi's face on hers, and with speaking, and it was just odd. Of course, Steve Buscemi's face is just weird, but it's adversarial networks are a big thing. And an example of where you're combining many different.
Do you think that adversarial networks are going to slowly take over most of the other machine learning methods then? Or is it just something that's useful in one area, not necessarily in another?
I mean, there's still the underlying core methods, right? Mm-hmm. And so it depends on the application, I feel. I've only seen these image recognition related applications. I was trying to train one for generating language, but that's a lot more complicated than I could appreciate, because you need many more examples of correct grammar, and it was spitting out nonsense. Yeah.
In terms of starting with something like this, there's the tutorials that are talking about TensorFlow, and trying to looking at also scaling it to a more of a real-world edge-based application. Mm-hmm. What do you recommend as how to start at the ball of whatever it is?
Just playing around. I mean, to get familiar with the methods, there are small and clean data sets that are out there, and I can recommend Kaggle. That's where in addition, when I started out, I just took a Udacity online course, just kind of curious about it, and then I went on Kaggle.com and started to look at their data sets, read through their forums, and try out what I started learning. And I started to learn more and more, and there you have small data sets that can be run on your local computer, laptop, and you get a better feel for what is possible. And you can build your own face detector, build your own OCR. You can, and then they have their own competitions that are actually paid, where I think one of them was predict whether a patient will, when the next patient will arrive at the emergency. And they have just, maybe not a million rows, but like in the hundreds of thousands of example data of when the next patient arrives, and then you have to predict the next one. And I found that a really good resource, also because there are forums, and it's just it's like the place to learn and chat and practice data science. It's a good reliable resource. But then there's more out there that I'm not aware of. I'm sure.
So then a follow-up on that would be, what would be the sort of base primitives that you would look to be in a computing engine, especially when you're downscaling it? So, I mean, there's the BeagleBone AI that has just come out with core processing engines. And you look at it and you go, oh my God, you know. Like, and
so
you
that,
look at other people starting with sizing, trying to size a set.
Yeah.
If you're looking at a certain set to depth of what could be supported, you know.
with hardware, I mean, yeah, I feel like with my work, because I'm not so involved in hardware, I just push it to the cloud. So the cloud services have lots of GPUs and machine learning as a service available that you can just rent a GPU. It does the calculation, or it does the training and everything, and then it sends you back the core model, which is less computationally intense. Running predictions is less computationally intense than the learning of it. But then that's also where, for the learning of it, you take it offline. And then when you want to house it in a hardware, then you don't need, it's not as computationally intensive. And so you don't need as big hardware. But don't quote me on that. I'm not a hardware person. Yeah.
Yeah, indeed. Oh, yeah, go ahead.
Yeah, the three types of machine learning there that is shown on your slide, is any one of them more dominant than the other, or is the trend today to combine them?
Combining them.
Combine them?
Yeah. I mean, each of them have their benefits and their applications. So I feel like I'm mostly working in this realm, even though I want to be working in this realm, just because interacting with your environment is so much more interesting and can result in interesting agent solutions. But I guess they all have their. I'd say that supervise is the most used, but I wouldn't. But it's still very dependent, I feel, on the other two as well. So combining multiple of these methods, you can make combining a supervised learning algorithm with a reinforcement learning algorithm, you get a much better game player. Combining unsupervised with supervised, you get a much better predictor. So it's definitely combinations are more the way of the future, I guess. But I guess if one was the one method is like a lot of people have things that they want to predict. So I'd probably go with supervised. Yeah.
Can you comment on what's being done among machine learning developers to sort of restrain the use of this technology by advertisers or other nefarious actors?
So I feel like because it's still a new field and a lot of people are not aware that so much is possible with it, there hasn't been enough data ethics for one, but also enough enforcement. either. So everything with Facebook and Cambridge Analytica is, okay, there's no rules in place, so let's see what's possible. And then only it's like, oh, we went a bit too far there, then an enforcer came and said, stop that. But I feel like there's no, all the data is out there and available, and each company is gathering their own data. It's cheap to store it, it's cheap to gather it. It's just that there's a lot of people that need to just process it. A lot of companies are being made from it. I don't have a, it's already happening, I guess is what I'm saying. It has been happening for many years. And how to kind of control it is make more people aware of it so that there's a bit more enforcement in place. Is how I imagine. Does that answer your question? It is a bigger like ethics question that I feel like it's more of a discussion.
Yeah, I mean, well, you're part of the community developing these tools. Like, is there a way to develop them in such a way that lends itself less towards some applications or more towards others? For example, like, it seems great that Netflix is going to recommend a show I want to watch until I'm like 4 hours into binge watching some series of shows, and you know, like, oh, okay, like the advertisers have enabled me to do something unhealthy for myself to their benefit. And they're the ones who have the money to kind of like make the most out of the tools to their advantage.
Yes.
So I'm just curious, like, whether there's any sort of like committees or organizations or groups within the machine learning development community that are trying to take steps to limit this type of use of the technology.
I'm pretty sure there are, but they'd probably be a not-for-profit, and they won't be as powerful as the profit companies. But yeah, I mean, there's like AI for good, and machine learning for the environment, and a lot of other things out there that are AI companies that are trying to be as ethically responsible as possible and enforce that in the wider community. But a lot of people are not receptive to that, I feel, unfortunately. Yeah.
There's sort of similar question in a way. 2008, we saw the crash of the markets, and a lot of that decoding it was attributed to the fact that the people behind the algorithms got ahead of really the people managing them. And the long tail of risk really got very long, so that there were a few people made a lot of money and a lot of people lost money. But looking at the business environment, which often says, you know, we've got a magic sauce for something, and then sells it, you know, as part of their product thing, which is the business side is different from the developers. What do you think I think it's the European side, the European Commission has come out with the statement that if you're making a product, you've got to be able to understand that product.
Oh, okay. Yeah.
So really it's in this artificial intelligence and in this combination of magic source, should you actually be able to say how that AI is working, that magic source. So if it's a matrix of deep learning, is it possible to characterize what's going on? And if it's an essential function of some sort, either like driving or predicting health outcomes, as opposed to just coming up with a Netflix suggestion, how much regulation do you see going on out there versus maybe is there a Wild West, or where are the areas that is of the Wild West? There's a sort of a wild side, and then there's some areas kind of clamping down a little bit, I think, like the Europeans. Really, it's fairly open-ended. Follow on from that question, really.
Yeah. It's exactly. It's an open-ended discussion, and I feel like it's important that people be aware that a lot is possible with the copious amounts of data that is out there and that people are gathering. So we did this one project. Wait, probably should not go into too much detail because we're being filmed. But but yeah, so there's we've seen how the data that you can gather. So the idea of personalized advertising. So just that, even based on your IP address, that is enough information to know what some of your behavior can be. It could be, you could already be bucketed based on your IP address, your location, you can get your location and other user information that might be able to help what kind of a consumer you are. And they might up the price if you're going to be spendy. So there's a lot of ethics in the field that it should be talked about more, definitely.
But the question is really, is it helpful to actually say when a product's being sold, so it's becoming at the business level, that it should be understood? There should be that if the people selling really don't know what's going on underneath the hood.
Yeah. If they're saying that it's magic, just algorithms or something like that. Yeah. No. I think that is good because they're saying. The hope is that they're at least saying how the data is being processed. What's the data that's being gathered, and that's the privacy policy, and how is it being processed? I feel that's where, but even how it's being processed, there's still the gap of what is possible with it. So from what I read of the Cambridge Analytica, they just gathered all the Facebook data of likes and responses and so forth, and they were able to create a psychological model of every person on Facebook. And so that's where it became very powerful, because all of a sudden you know what they are, but who would have thought that was possible with just a few likes and posts? It's like, okay, they can tell you that we're processing the data in this way, but to know that it's possible to swing people's opinions, that's a much that's something that maybe the seller wouldn't necessarily know. You should hope that they know. I should hope that they know. Yeah. Yes.
So Amazon was in the news not too long ago about an AI algorithm that they had used in their human resources department to be able to take incoming resumes and be able to vet out certain people, and they would have they would just interview certain, that.
Yeah, so they have a probability model of this person is more likely to come on board, kind of thing. Yeah.
And what was interesting is they were finding that the AI algorithm was actually not choosing women to be processed.
I think I heard about I heard about this as well. Yeah.
So it was really interesting. Like, how would the algorithm have kind of picked up on that? Is it because the sample resumes coming in, they were from this?
I suspect it's because of historical data, and they've gone very far into the past with historical data, and it's much more recently that there's been a bit more equality with respect to male-female hires, whereas back in the 60s, it was probably a lot more male-centric. And so it's trained itself on that past data and not on the more recent. It's treated it as equal weight, even though, but potentially, but also with that, it might just depend on what the data looks like.
It's interesting. I don't know what they actually used, if they were included personal information like their name or so forth, but it's really interesting how it actually developed.
Yeah, exactly. Was the AI told what gender they were, for example? Was it completely biased already, or was it completely unbiased? So yeah, there's a lot of questions that I'd have about what was the sample data that was used to train it, and so just from just hearing that, it's like, it could have been just that it was something to do with the historical data, but it could be that, it all depends on what the input data is, and whether that input data is biased already. So, yeah.
All right, it's now 5:30, and I'd like to thank Dr. Jamshidi for his very impressive and instructive talk. So let's give him a round of applause.